Who remembers Merkle's puzzle I mentioned last week? What was the specialty?
It's hard.
Yeah, it was hard. Yeah. Especially for the eavesdropper.
It's hard to understand.
It was hard to understand. Okay,
It's struggle.
but it is a big step forward. Like before Merkle's puzzle, if you wanted to exchange information, you had to basically put it in an armored van with some security guards with guns on the top. There was no way of exchanging information using public infrastructure, which could be the internet, which could be a telephone line, which could be just sending something down the road, because somebody might capture it, on the road, over the telephone line, over the internet, and would then have all the information. So Merkle's puzzle basically showed publicly, because there were some attempts earlier, and this whole idea actually was already discovered in 69, I think, at GCHQ, but they kept it a secret, so nobody knew about it. But this was the first time people publicly showed that it's actually possible to transmit a message using a public infrastructure, and the message that you transmit will actually be secure, or will be secure to some extent. Okay, let's try to explain Merkle's puzzle again. And because I haven't used this drawing function since last week. Yay. Okay, so this is the picture we drew last week. So we've got A and B, or in cryptography we always call them Alice and Bob, and they want to exchange information using a public infrastructure. Send the message down as a letter. You see, letters aren't safe. There were some countries that made whole task forces out of this process of opening letters that were sent to their embassies and then closing them again. So letters aren't safe. Sending something down the road isn't safe. Telephone isn't safe. Internet isn't safe. But Merkle had this idea that if we want to exchange a key, and this key could then be used for something else like Visionaire cipher or whatever it might be, we could actually send it down using public infrastructure from Alice to Bob, and even though Eve might be listening in, Eve still has no clue. So what we need for that is we need a way of packaging up the message we are going to send. And packaging my message up takes a short time, but unpacking the whole thing takes a long time. Think of some sort of puzzle, some sort of quiz. It's easy for you to think of it, but it must be difficult for the other side to solve it. So for argument's sake, we can say it takes an hour or it takes 10 hours to solve it. It doesn't really matter. So what we do is, as part of this puzzle, we take our key and we wrap it up as a puzzle, and we put some sort of identifier in there as well. If I do this once, I wrap my key up as a puzzle and I send it down from Alice to Bob. Eve might have secretly caught this information. So Eve can solve the puzzle, Bob can solve the puzzle. Both sides have the same kind of effort to solve the puzzle. So we haven't anything gained so far. But the gain we get is if instead of sending one puzzle down the line we send down 1,000 puzzles. Now Bob has 1,000 puzzles, for argument's sake. Yeah. Eve has 1,000 puzzles. If they wanted to solve all the puzzles, would be the same kind of effort on both sides. But now Bob just randomly picks one of the 1,000 puzzles and solves it. And after Bob solved the puzzle, he gets some sort of identifier. Let's say 254 and whatever our key is. Yeah, this is supposed to be my key. So Bob only solved one puzzle, and now Bob can basically tell Alice, I want to use the key 254. Now Bob knows key 254 looks like this. Alice knows key 254 looks like that. Bob has all the 1,000 puzzles, but Bob doesn't know which of the puzzles contains the key 254. Eve doesn't know. So Eve has all the puzzles, but hasn't solved any. Eve knows the puzzle is 254, but Eve doesn't know which of the 1,000 puzzles contains 254. So what does Eve have to do to solve the puzzle? That contains 254.
Well, randomly go through them all.
Yeah. And if Eve is lucky, the first one will be correct. If Eve is unlucky, the 1,000th will be correct. On average, it might be the 500th time. So we've got a situation now where we can send information down the line that is publicly accessible to everybody, and even though people might be listening in, they still don't know what the key is. Yeah. So for the first time we had a situation where we think we can send something down over a public infrastructure. Yeah. Think of the one-time cipher. Was great, was secure, but the problem was, how do we get the key to the other side in the first place? And now suddenly, 1974, we've got a way of sending a key over public infrastructure, and even though people might intercept it, it's still safe. Any questions about Merkle's puzzle? Yeah. That's
so,
not so.
Yeah. So.
Yeah.
You've got a key. So B tells A that, like, I've got key number 254.
Mm-hmm.
So A now sends the message.
Yeah, encrypted with whatever this key is.
Right.
That is linked to 254. So this is only a way of exchanging a key. It's not a way of encrypting the message. We still need then something else. For argument's sake, Caesar cipher probably wouldn't be worth the effort, because Caesar cipher, will be easy to decrypt. Yeah. Or we could do something more complicated. So we can only exchange keys this way. We can't encrypt. And with this in mind, Diffie-Hellman came up with an even better way of exchanging keys. Let me switch back to this other mode. Well. Come on. Here we are. So. Okay. Yeah. So 1974. Suddenly we knew that actually we can exchange a key using public infrastructure, and that set a whole sequence of events in motion where this was being improved and got better and better. And not long after, 1976, we had Diffie-Hellman coming up with the Diffie-Hellman key exchange. Like Merkle's puzzle, You can only exchange keys this way. But the next way is much more clever. Because what's the problem with Merkle's puzzle? It's quite wasteful. We have to come up with 1,000 puzzles or 10,000 puzzles or however many, and most of them will be disregarded. So there's a lot of effort put into the system that is wasted. I mean, it's not really wasted because it's necessary so that Eve doesn't get to the key, but there's a lot of work involved that doesn't directly lead to anything. So Diffie-Hellman, they knew about mathematics, and they found a way of linking something that happens in mathematics with this kind of concept. And this is a theme that's being repeated again and again. Why is Google so big? Basically, the guys behind Google, they knew about mathematics, and they knew about something that occurs in mathematics that they thought might be quite useful to create a better search engine than what has been around at the time. Who remembers a time before Google was popular? Which search engine did you use?
Ask Jeeves.
Ask Jeeves, those kind of things, yeah.
Terrible.
Yeah. So I think the first time I used Google was in the late 90s, and before that there were things like Alta Vista. They were quite popular and they were good, but Google then became much better because they used a mathematical concept, they applied it, and it was much easier to then basically have good results. And we've got the same situation here. Mathematical concept being applied, and this is a concept where I completely simplify it, but it doesn't matter because we're not studying mathematics here. But there's some sort of one-way street in mathematics, or in parts of mathematics, where you can do a calculation in one direction, and it's extremely difficult to undo the whole thing, to go back the other direction. It's some sort of mathematical one-way street. Now actually it turned out that 7 years later Malcolm Williamson from GCHQ came up with nearly the same idea. But we all know what GCHQ is. Yeah. So with it being GCHQ, obviously they kept it a secret. So Diffie-Hellman, when they came up with it, they made this knowledge public. And actually, when you use a web browser, when you use what's used to be called SSL these days, officially it's called TLS, but we still call it SSL. When you see the log in the address bar of your browser, actually this Diffie-Hellman mechanism from '76 under certain circumstances can still be used, even though it's more than 40 years old. Okay, let's have a look how it works. And I'll try to be very light on the mathematics. Okay, we've got the same situation here. We can exchange a key using an insecure communications channel. And we need specific kind of numbers, and again I'm keeping it very light. But we all know what a prime number is, yeah? Can one of you just tell me in one sentence what's a prime number? Prime number can only be? Yeah, very good. I mean, you could divide it by something else, but then you've got a remainder left after the calculation. And that leads directly to modulo. Modulo is basically you do a division, and the modulo is the remainder of the division. So example is 23 modulo 7. What's the answer? Yeah. So 7, 14, 21. Yeah, 21 we wouldn't have any remainder. 22 the remainder would be 1. 23 the remainder is 2. Yeah. So modulo is the remainder of a division. So before I show this, let me just, before we do it the mathematical way, there's a nice way of showing it using colors. let me just show you the color explanation. Just need to look where I put the picture. I mean, we are all familiar with mixing colors, yeah? There are two ways of mixing colors. Yeah, additive and subtractive. Where are my pictures? The network connection is very slow. Working on it. Here we are. Okay. Yeah, it doesn't matter which way of mixing colors we use, but basically in this color explanation, we've got a common paint, in this case yellow, and Alice thinks of a secret color, Bob thinks of a secret color. So the common paint, we can let everybody know about it. Yeah, I can tell everybody over some sort of public infrastructure, my common paint is yellow. Then Alice thinks of a secret color, Bob thinks of a secret color, and they mix the colors. Yeah. So here yellow and dark orange is light orange. In this example, yellow and green is blue. Yeah. Now Alice can basically send her color that is mixed over the public infrastructure, and Bob can do that. Yeah. And the exciting thing here is now, if Alice mixes Bob's color with her own color, or if Bob mixes Alice's color with her own color, they come up with the same hue. Yeah. Because in both cases we got yellow plus orange, yeah, plus in this case green. But we didn't get this shade of green directly, we got it through Bob's mix. Yeah. So in both cases, yeah, this shade of, let's call it brown, yeah. What components are in this shade of brown? You tell me. And how many units of each? Yeah. So we've got 1 unit of yellow, 1 unit of green. Yeah, they became this, and 1 unit of orange. And here, yeah, we've got exactly the same 3 components. They were just mixed in a different order. Now, obviously, this wouldn't be that secure, because when I see this shade of color and I know the common paint is yellow, I can figure basically out from color tables what I had to mix in to get it. But the point here is, I've got a common color, I mix something in for myself, I hand it over, they mix their own component in, and in the end, yeah, we've got our common secret. If somebody listens in, all they know is the common paint and Alice's mix, and if you listen in the other way around, you've got the common paint and Bob's mix. But what you don't have is the secret color or the common secret. Okay, let's go back. Now, okay, so first to do it mathematically. Alice and Bob, they need to agree on some sort of prime number and on a base. So in this case, randomly picked 23 as our prime number and randomly picked 5 as our base. So using the public infrastructure, Alice and Bob basically say our prime number P is 23 and our base is 5. So if there's any eavesdropper, they know this information now. And they know P is 23, G is 5. Now Alice will think of her secret number, and now she will take the base, which is publicly known, to the power of her secret number, modulo 23, and the result is 8. So Alice will say, yeah, I did the calculation. Yeah, I thought of A, but it's a secret. But G to the power of A modulo P, the answer is 8. Yeah. Now if somebody's listening in, yeah, the remainder of a division is 8. There could have been many numbers we might have fitted into this equation to get a remainder of 8. So we don't know what they fed into this equation. Because there'll be at first glance there'll be a lot of numbers I can feed into this equation so that I get the remainder 8. Okay. Bob does the same things, thinks of a secret integer, does the calculation, and sends it over to Alice. So if anybody listened in, they know P, the prime number, they know G, the base, and they know the result of each calculation. But they don't know what each side fed into the calculation. But now Alice can take Bob's output. Bob's output was 19. Alice's number was 6. So you take the output of the other person to the power of your own number. You do the calculation and you come up with a number. Bob does the same. Bob takes the output of the other person to the power of the own number and comes up with the same secret. So now Alice and Bob, they both know the key is 2. But if somebody was listening in, they still don't know what the key is. Yeah. Because they have the two results of the calculation, but to get the key, they need the input and the result from two different sides, and they don't have the input. So Alice and Bob, they have the same key. In real life, obviously, you would use bigger numbers. You'd think prime numbers, they get more and more scarce, but there's a whole branch of science, more or less. I mean, I'm exaggerating when I call it a branch of science, but there's a whole army of people just busy finding higher and higher prime numbers. Yeah. And computers are pretty good at coming up with prime numbers, and the ones we can work with, they are high enough so that this whole Diffie-Hellman key exchange is more or less extremely difficult to come by. Now, if you calculate, if you try long enough, you will find the solution at some stage. But if you did some online shopping today and you entered your credit card number and somebody intercepts this information and now tries to work out what your secret key might have been, if they try hard enough, they'll find the answer. But if they find the answer in 15 years, by that time it doesn't matter anymore what credit card number you entered today. Yeah. So if people really want to find out, if they put enough resources in, they will find out. But obviously the point here is, by the time they find out, is the information still that important, or did it become more or less meaningless? Now, if you're obviously some sort of government with huge resources at your disposal, and you were to decide to use all your resources on solving this specific mathematical problem, then they would be able to do it pretty quick. But that would also mean that whoever it is who has all those resources at their disposal, they must be pretty big, they have tied up their resources solving this mathematical problem, and they can't, they can't do the same thing for any other decryption that might be going on. Yeah. So just because you might think a government has lots of superpower computers, they could set them to work on decrypting the information, but they would waste all their super computer powers on that specific case. Yeah. They couldn't do it for everybody at the same time. Okay, let's have a look. In case you want to try this out yourself, there's a nice web page. No. And I can think of a random number. Okay, let's try it out. So you think of a random number.
6.
6, okay. You think of a random number. 7. Okay. Yeah. Maybe I need another browser. Let's try Chrome. Sometimes by default. Okay, let's try Chrome. Okay, well, 6 and 7. It doesn't work anymore. Shame, shame, shame. Strange. Okay, sorry I can't show you. But what we would have gotten is, with our own input and the number from the other person, we can encrypt something, and I can then send the encrypted message over, and the other person can take the opposite numbers and can decrypt the information. Well, shame it doesn't work. Okay. Diffie-Hellman, we can just exchange a key. Yeah. We then still have to use the key and put it into something else. For example, Caesar cipher, Visionaire, or whatever it might be. We can't really encrypt messages. Let's go back one step and let's do so we've got Alice and Bob. So both of them had a number they kept secret. Let's call it a secret key. And both of them had a number they made public. Let's call it a public key. Yeah. How can we use those keys? So before I go into more detail, I'm gonna show you the next slide. But have you heard of public key and private key before? Yeah? No? Public key cryptography? Okay. So RSA is what came next 1 year later, 1977. And this is still the bread and butter of cryptography. So again, we've got specific numbers, prime numbers involved again, modulo involved again. And how does it work? We've got two prime numbers. We think of two prime numbers. In this case 11 and 13. And I multiply them with each other. Yeah, and I'm gonna make this public. Yeah, so you think of two prime numbers, you multiply them with each other. This is gonna be your public key. You then choose an integer. It has to be basically a specific number. You can't take any number. And basically in this case it has to be smaller than 11 minus 1 times 13 minus 1, but it has to be co-prime to that number. It doesn't really matter. Let's forget about the mathematics, but that number needs to basically follow specific mathematical rules. And that's some sort of number we can make public. Yeah. So we've got two numbers we can make public, and we've got one number we keep private. Yeah. And again, it follows some mathematical requirements here. The nice thing now is we can encrypt a message. And let's go back a few slides. Let's go back to what we did last week. Look at this message here, meet me at Harris Building. Think back here. Yeah, we talked about how a letter will be encrypted as a binary number. Yeah. So a message is basically, in my message, basically every letter represents a number, and to write down the whole message, I write down all those numbers next to each other. So basically this message, meet me at Harris Building, is just a very long number. Yeah, I could take this binary number now and express it as a decimal number. So my whole sentence, I could express my whole sentence as one number. You could write a dissertation in your final year, and the dissertation could be thousands and thousands of letters long. I can just write them down as a binary number. Your message would just be a very long sequence of zeros and ones. And, you know, because we humans are used to thinking in decimal numbers, not in binary numbers, it's just a number. We could as well convert the binary number to a decimal number. Yeah. You could express your whole dissertation, you could express the whole Harry Potter book or whatever it might be as one long number. Yeah. So in the end, in modern cryptography, messages are just numbers. So what can we do now? We have a message we want to encrypt. It's just a very long number. Now let's go back to RSA. So I can just take this message to the power of e, which I made public before, modulo n, yeah, which I also made public, and I have encrypted my message. So I take a message and I can use those two numbers that I made public, and it's been transformed into another number. Yeah, that's the easy part. How can I get this new number back to back into its original form. To do that, I need D. But I never told anybody else how D works. Yeah. That means everybody, because I made N and E publicly available, everybody can take a message and can transform them into some sort of other message. Yeah. Which, let's call it C. But the only way of getting this message back into its original form is if you know D, which is my private exponent. So I take the encrypted message, the ciphertext, to the power of D modulo N. Yeah. And then I've got my message decrypted. So N and E are public. So who can encrypt? Let's say I come up with N, E, and D. Now, I put N and E on my Facebook account, or on my Twitter account, or wherever. So you all know my N and my E. So all of you could send me a message now. You write a message, you encrypt it with my N and with my E, and you can put it out on the internet, and everybody in the world can read the answer here. But who's the only person who can decrypt that message? Only person who can decrypt the message is me, because I'm the only one who knows D. Yeah. So let's go back to our picture. Yeah. So Alice and Bob, yeah, they've got their private key and they've got their public key. So Alice can put her public key on the internet. Bob can put his public key on the internet. And there's our naughty Eve again. So Eve knows Alice's public key and Bob's public key. Alice wants to send Bob a secret message. What does Alice do? There are 4 keys here. Which key does Alice use to encrypt the secret message to Bob?
Does she need the other one's private key?
Alice needs Bob's private key. Now, if you encrypt something with Bob's private key, which key do you need to decrypt it? If you encrypt with Bob's private key, which key do you need to decrypt? Bob's public key. Who has Bob's public key?
I mean everyone.
Everyone. So, not the solution. Because A, Alice doesn't have Bob's private key, and B, then everybody could decrypt the message. But let's go a step back. What you suggested is actually very good in another way. Okay, let's go back a step. We encrypt a message with Bob's private key. So which key do you need to decrypt it? We encrypt a message with Bob's private key. If you want to decrypt it, which key do you use? No, I encrypt it with his private key.
Yeah.
Then you decrypt with his public key. Yeah, so I feed a message in. Hello. I encrypt it with his private key. Out comes X, Y, Z, K, Z, whatever. So I encrypt with his private key. Which key do I use to decrypt? His public key. Can you see any real world use for that? What's the advantage of encrypting a message with Bob's private key? Let's go back to the beginning of last week. Aha! So, what's the advantage of encrypting a message with your own private key?
Authentication.
Yeah. If I encrypt a message with my private key, you can all decrypt it, because my public key is on the internet. But the thing is, you can now be sure that it really came from me. Because the only person who has my private key is hopefully me, which means if you can decrypt it with my public key and it makes sense, it was encrypted with my private key, which means you can be sure I sent the message. Yeah. Now instead of what people do is, instead of encrypting the whole message, they take some sort of short version of the message, some sort of checksum or hash, whatever we call it, and we just encrypt that bit at the bottom. Yeah. We take some sort of mathematical function to make the message really small. Think of creating a zip file. A zip file makes things small. It's a bit like that. You basically make a zip file of the message, you compress it down to some extent. You could unzip it, you've got the original back. So I've got a smaller bit of email. I encrypt it with my private key. Everybody can now basically, I just attach it at the bottom of my email, and now everybody can be sure that I sent the email. So nobody can pretend the email came from me when it actually didn't come from me. So you can get those mechanisms. A very popular one is PGP. Or there's a publicly available version that's free called GPG. Yeah. Was very popular in the past. These days it's not that common anymore, because people just couldn't be bothered with the fuss. They think, why do I need to know a message is from a specific sender? So in private correspondence people don't really do that. But if there's some sort of business case use, this might be popular. Or what's also common these days is that your email provider can do this for you under certain circumstances. So if you use Gmail and you send an email to another Gmail address, then Google can basically check whether the message really came from that person, and it will let you know. But if you need to ensure a message came from a specific person, you can just install a little bit of additional software, and you can do that yourself. Let's go back to this. Yeah. We also call this an electronic signature. Yeah. Have you heard electronic signature? Yeah. So basically we make sure our electronic signature does not mean we write our signature on a sheet of paper and we scan it in with a scanner and we put a scan of our signature on a Word document. Some people think that's what it means, but actually an electronic signature is some sort of electronic proof that the message came from a specific person. Okay, so Alice wants to send Bob a secret message. Let's go back to my original question. There are 4 keys here. Which key does Alice use to send Bob the message? Okay, Alice wants to send Bob a message. There are 4 keys here, but Alice only has access to 3 of those 4 keys. Which 3 keys does Alice have access to? Her private key? Her public key? Bob's public key, yeah. So so she can't encrypt the message with Bob's private key because she doesn't have access. So 3 keys left. Alice wants to send Bob a secret message so that only Bob can read that message. And if Eve intercepts the message, Eve can't read the message. Which key does Alice have to use? Her private key. Okay. If she encrypts a message with her own private key, yeah, she writes hello. She feeds it into a private key, out comes something else. Yeah. Now Eve can intercept that message. Which key is being used to decrypt the message? Her public key. Does Eve have her public key? Yeah. So it didn't work. Let's try that. Okay. Okay. Alice takes Bob's public key. Yeah, she feeds something in. Hello becomes something else. Okay. Eve gets it. Which key do we need to decrypt the message? Bob's private key. Bob's the only person who has this private key, so that works. Yeah. So now Alice and Bob can exchange messages with each other, and nobody else who captures this information can decrypt it. If we all have a public and a private key, I can send a message to any one of you. Let's say I want to send a secret message to you. I take your public key, I encrypt the message. I can put it, on my Facebook page. You can all read the message, the encrypted message, but only you can decrypt it, because only you've got the key. But we can also create an electronic signature if we do things the other way around. So the whole thing is very clever, and the whole thing is basically what we use when we enter our credit card details online, when we do online banking, anything like that, we're using public key cryptography. Yeah. So every time you go to a web page and you see the little lock in the corner, it basically means that the web page is encrypted. So your web browser was talking to the web server in the beginning. They were exchanging some keys, and they came up with a way of encrypting the communication. And if people listen in to that message, because you use Wi-Fi, they can listen to your Wi-Fi signal. They still don't know what the message is, because they don't have the keys. Now again, if you spend enough effort, you can decrypt the message, but yeah, for argument's sake, if it takes 10 years and they have some computers working overtime for 10 years so that they can just figure out what you wrote 10 years ago, is it worth the effort? Probably not. And if your message is so secret that 10 years isn't good enough, you can just use bigger prime numbers, and the whole thing will be more secure. Yeah. When we talk about cryptography, we always talk about how long the key is we used to encrypt it. And that goes back to the binary numbers. I hope you remember binary numbers. Yeah. One binary symbol, one binary digit. How many possible combinations? 2. And 2 binary digits? 4. Yeah. And 3?
8.
8. Very good. So 128-bit key, for argument's sake, does not have twice as many combinations as a 64-bit key. Yeah. A 65-bit key would have twice as many combinations. So hacking a 65-bit key takes twice as long as hacking a 64-bit key. Hacking a 66-bit key would take 4 times as long. 67-bit key would take 8 times as long. 68-bit key would take 16 times as long. Yeah. So how many more combinations in a 128-bit key than in a 64-bit key? It's a number with nearly 20 digits. I don't even know what to call it. 1 with 6 zeros is a million. 9 zeros is a billion. 12 zeros is a trillion. Don't know how this continues. But it takes trillions and trillions and trillions times longer to decrypt a 128-bit key. Not safe enough? Use a 256-bit key. Yeah. Even more trillions and trillions and trillions times longer. Yeah. Just the change from 64-bit keys to 128-bit keys. Yeah. 10 to the power of 19, that's already more than the diameter of the Milky Way galaxy. Yeah. So we're talking about huge numbers here. On the other hand, humans are good at making a mess. Hyperinflation in Zimbabwe. Some economists think that in 2009 the inflation was a factor of 10 to the power of 20. So we can always come up with bigger numbers, I guess, is the lesson to learn here. Okay, any questions? Anything you'd like to ask? Okay, thank you. See you next week.